and the zeroth law of thermodynamics. We also talked about the ideal gas law, temperature, pressure, volume, and the number of particles, which are thermodynamic parameters of the states. And we talked a little bit about the physical motivation at the microscopic view to motivate the ideas of temperature and pressure. This time we're going to talk about a model system of using gas inside of a piston. And we're going to talk about how we can use PV diagrams, pressure volume diagrams, in order to understand the states of those systems, of the system of the piston. We'll also talk today about how you can transfer energy through heat and work, and how these can result in the first law of thermodynamics, which is an equation that is a conservation of energy equation. And we're going to talk about some different thermal processes that you can have with ideal gases and using this piston in the PV diagrams as motivation. We're going to talk about isothermal, isobaric, isochoric, adiabatic. So let's talk a little bit about our model experimental system. This is, again, much like how you have a mouse model or a fly model. In this case, the model that we're going to use, which is a simplified system, is a piston filled with an ideal gas. And so the piston looks like this from the side. It's actually a cylinder full of these gas molecules. From the top view, you can see it's a round cylinder. And these are supposed to be similar to the cylinders like you would have in a car, where you have inside your combustion engine. So some of the things about this system, it has many particles, so we mostly talk about moles. So it's a macroscopic amount of particles, and so we can't see the individual particles. We'll just assume that they're acting all together as an ideal gas. The particle number is constant, so that's conserved, and usually if the piston is filled, a conserved quantity for the number of particles. And the piston can be isolated, meaning that you could insulate it so that heat cannot go in or out, or it can be in contact with a thermal reservoir, which will keep the temperature constant. And finally, this top can move up and down to change the volume and the pressure of the gas that's inside, and this is how you can change it. And another way to think about a piston is like a bicycle pump. That's another good example of a piston that you've come into contact with every day. In a bicycle pump, as you push out, you push down on the piston, you're decreasing the volume and you're increasing the pressure. It goes through a cable and then increases the pressure in your bike tire, but it's the same kind of idea. And so we can talk about the number of particles, the volume, the temperature, and the pressure of the gas that's inside of this. And we can obviously make changes to this to go through the thermodynamic processes that we'll talk about today. So using this piston as our experimental system, we can then deduce the pressure and the volume of that system. And for any particular state, we can plot on the pressure volume or PV diagram the location of the pressure and volume of that state. If we and then we can use the ideal gas law to get from that pressure and volume to the temperature. And again, for most of our systems, the number of molecules is not going to change. If we then push down on this piston so that we have a different pressure and volume, we get a different temperature, and we can plot the pressure and volume on this PV diagram. The number of molecules again is going to be the same. In this case, we can see that the pressure has gone up as we push down on the cylinder. The volume has gone down, and the temperature could go up or could go down. It just depends on the exact changes that have been made in the cylinder.